In this problem, we're given n cities, m roads, and a capital city S. And we want to construct the least amount of new roads such that the capital city can access every single city. So let's look at an example. There was an audio issue, so I have the working code, which I will go through later, but let's go through an example first. So the one key thing that you have to know is that for every pair of edges that are given, which signifies a road, so this means that city 1 can access city 2, but this does not mean that city 2 can go to city 1. For that to be true, you would need one more edge to 1. So this is a directed graph. So let's have an example. So let's say from city 5 you can access city 1, and from city 1 you can access city 2. And then let's say from city 3 you can access city 4, and then from city 9 you can access city 6, which can access city 7, which can access city 8. And then let's have a cycle, right? So let's have a 10 links to 11, which then links to 12, which then links back to 10. So this is like a cycle. So, and let's say our capital city is 7, right? So I'll just put 2 asterisks around it. So as of right now, 7 can only access 8, and it can't access any of the other cities, right? So we want to add the least amount of roads, right? So first thing first, let's take away the current capital city and all the nodes it can visit, because we don't do any changes because we can access all of them right now. So as of right now, we don't need, okay, let's just cut it out for now. Actually space it quite a bit, like that. Okay, so we're only focusing on this. So now we can see there are clearly 4 components, all right? So this is 1 component, 2, 3, 4. And what we can do is we can obviously see for at least these 3, there is a head node such that this 5, such that if we connect this capital city to 5, it can access 1 and 2, right? Like for example, if we link the 7 to the 1, yes, we can access 1 and 2 now, but we don't have access to 5. Whereas if we link 7 to 5, we can access 5, 1, and 2. So the head of each component here, of each of these trees, would be 5, 3, and 9. And now in this cycle, there is no head because they're all linked to each other. So what we can do instead is we can just pick one node and say, okay, let's say this 10 is the head, and this 10 has access to all the other nodes. So in a cycle, we can just pick one node at random, and that doesn't matter. So now that we know, the fastest way is to link the 7 to the head of each of these components. So how do we do this? So what we should do is we should be aware of the DFS finishing time. So now what does that mean? So let's have a stack which is initially empty, and now let's go from 1 till 12, right? Okay, so have we seen 1 before? No, so we'll add it to the stack, and then we'll visit all the other nodes that 1 can visit. So that'll be 2. So next we go to 2. Have we seen 2 before? Yes, we have, because 1 has access to 2. So we don't do anything. Have we seen 3 before? No, we add it here, and then we go and visit all the other nodes 3 can visit, which is 4. So have we seen 4 before? No. Oh, sorry, yes. So we do nothing. Have we seen 5 before? No. So we add 5, but we've seen 1 before, so we just stop there. Have we seen 6? No. 7 and 8, let's assume we've seen them for now, so we don't care about them. So now we skip to 9. Have we seen 9 before? Nope. Have we seen 10 before? Nope. Have we seen 11? Yes, because when we saw 10, we made sure to visit all the nodes it can. So we went and saw 11 and 12. So therefore we've seen 11 and 12, so we don't add them to our stack. So currently our stack is like this. So now let's go from the top to the bottom. So have we seen 10 before? No. So we add 1 to our answer, so now it's 1. And we take it off, and because of that, we've seen this major component. Okay? Have we seen 9 before? No. So we increase our answer by 1, and we take away this whole component. Because essentially what we can do is we can just link the 7 to the 9, and then we have access to that entire component. Have we seen the 6 before? Yes, we have. So we don't do anything at all. Have we seen the 5? No, we have not. So we increase our answer by 1, and we take away this entire component. Have we seen this 3 before? No. So we increase it again by 1. We take away this component, and this is gone. And now have we seen the 1 before? Yes, we have. So our final answer is 4. And so that's how we'll solve this problem. Okay, so how is this done? So this keeps track of whether we've seen a node before or not. And then this matrix of vectors will keep track of this graph. So over here, when I read in the n, m, and s, I do minus minus s to 0 index everything, because everything that's given is 1 indexed, and it just, for me, it's easier to work with the 0 indexed. So now for each road, we're given a, b, such that city A can go to city B, but it's not needed that city B can go to city A. So then in the location of A, we push back the vector B. So now we know that city A can access city B. Then we visit all the nodes that we currently can from our current capital. So in the example I just did, so that would be all the node that the 7 could access. So now we've seen all of those, we don't really care about those. So now we do the DFS visiting time, which is done through DFS1. So what is that? So if I've not seen a node before, I will push it onto the stack, and then for all its neighbors and all its neighbors' neighbors and so on and so forth, we'll run a normal DFS such that we will not push it onto the stack, but we will make sure we've seen it before. And the only difference between these two is we just add stack.push here. So we only add the first one we have not seen onto the stack. Right? And then once that's done, we just run this DFS. And in this DFS, all we do is say that if we have not seen a node before, we'll go and see it, and then we'll go to all its neighbors, and we'll make sure to see all its neighbors, and so on and so forth, until we reach the very end. So that's what that does. So after we do this, we now have our stack in the right order. So we just reset this array completely. So let's assume we've not been to any of the nodes at all, and we just go through the stack from top to bottom, and we check if we've seen the node at the top, and if we have seen it, we just move on to the next node in the stack. But if we have not seen it, then what we do is we're like, okay, this is the head of a certain component in this graph, so we increase our answer by 1, and we'll visit all this node and all its neighbors. And then you keep on doing that over and over again, and then at the very end, you'll have your answer. And yep, that's how you solve this problem. And yep, I got it accepted. So voila.